Welcome to this video on Year 2 Mechanics Chapter 4 Prep Practice Test on Moments. So question 1 is about the moment of a force. Now you're probably familiar with the fact that the moment of a force is the size of the force, magnitude, times the perpendicular distance from the perpendicular axis. However, if the information we have doesn't give us the perpendicular distance, we have to use some trigonometry. And there's a choice, really. Either we can find the perpendicular distance, or we can find the perpendicular force. So in this case, if you look at this diagram, and you see that the distance from the axis that we're going to take moments about x, if that distance is d, but the actual angle that the force makes with that distance is theta, then we can calculate the perpendicular distance as being d sine theta. That's this length here, which is perpendicular to the line force. So we can think of the moment of this force as F times the perpendicular distance d sine theta. So that's one way of thinking about it. The other way of thinking about it is that rather than finding the perpendicular distance, we can find the perpendicular force. So F can be resolved into two forces. One force that goes through x, which will be F cos theta, and the other force, which will be perpendicular to the line D, which will be F sine theta going up here. And so then, for that force, the magnitude of the force will be F sine theta, and the perpendicular distance will be D. So that's why I've written here, either resolving D or resolving F. In my experience, when it comes to second year mechanics problems, it's usually easier to resolve the force. Okay. So I'm thinking here as F sine theta times D. Anyway, the moment of this force about this axis x with the angle theta and the distance d is Fd sine theta, whichever way you think about it. Question 2. A horizontal light rod is held in equilibrium by three forces as shown on the diagram. So don't think of weight or anything else. These are the only forces. In fact, I suppose F1 could be a weight. So we're given 6 newtons up, F1 down, and F2 up, and we're given the locations. And we're asked in part A to consider moments about A. We could have taken moments about other points, but the question asks us to take moments about A. When taking moments, I like to give the direction. So in this case, I'm saying I'm taking moments about the axis A, and I'm going to take clockwise moments as being positive. That means that the 6 Newton force, if I think about what the 6 Newton force does about A, it's trying to turn this rod anti-clockwise about A, and therefore the moment of the 6 Newton force clockwise is -6 times the distance 1. F1 is distance 3 away from the axis A, and so its moment is going to be F1 times 3, and because it's clockwise, that'll be plus F1 times 3. F2 is distance 6 away from A, and it's trying to move anti-clockwise, so its clockwise moment will be minus F2 times 6. And if the rod is in equilibrium, the sum of all the moments must be equal to 0, just as when we were resolving the resultant vertically or resultant horizontally, the resultant in any direction is also 0. We can now use, in moments, we can use the fact that if something's in equilibrium, the total turning effect, that is the total moment about any axis, is going to be 0. And if we work this out, we get -6 plus 3F1 minus 6F2 equals 0. If we divide by 3 and rearrange, we get F1 minus 2F2 equals 2. And now for part B, we're asked to find the magnitude of forces F1 and F2. Well, if we additionally work out the by resolving the forces vertically, there's no point in doing horizontally because there's no horizontal forces, we get that vertically upwards we have 6 minus F1 plus F2, and because it's in equilibrium, the resultant must be 0. So that means F1 minus F2 equals 6. And now if we solve these two equations simultaneously, then we can work out that F2 equals 4 and F1 equals 10 newtons, and we're able to solve this problem. And this is a very common technique for solving mechanics problems, is that not only can we resolve, but we can take moments. Question 3. Now we have a non-uniform rod With a uniform rod, you can assume that the weight, if you're given the mass, you can calculate the weight, will be acting at the center of mass. However, if it's a non-uniform rod, that basically means there's more dense material in one side than another, or there's something attached, and so we cannot assume that the weight acts in the center. So this rod is 6 meters long. We cannot assume that the weight acts 3 meters along from the end or in the middle. So here we're labeling it as just being X meters long because we don't know how far along the rod it is. It rests on supports at C and D, where AC equals 1 meter and AD equals 4 meters. The magnitude of the reaction forces at C and D are 50 newtons and 10 newtons. Okay, so the rod feels these reaction forces upwards from the contact with these supports. And now we're asked to work out the weight W and the distance X of the center of mass of the rod from A. As usual, we can resolve and take moments. And because all our forces are only vertical, we can really only resolve vertically. In general, you can resolve in 2 directions. But in this case, we can resolve vertically, and we get, if we resolve vertically upwards, we get 15 plus 10. That's the 2 reaction forces from the support, minus W equals 0, which means we can immediately calculate that W equals 25 newtons. So that was nice and easy. And now if we take moments about some location, for example, A, it could have been about C or about D, but I'm taking clockwise moments about A, then we can see that the 15 Newton force has a moment of minus 15 times 1 clockwise, because it is in fact anti-clockwise. The weight has a moment of W times X, where X is the distance from A. And we know that W is 25 newtons, so we can replace the W by 25. And then the 10 Newton force is 4 meters from A, and therefore its turning effect will be 10 times 4, but its anti-clockwise, so it'll be minus 10 times 4. If we rearrange, we get that X is 2.2 meters. And then for part B, we're told that a mass of Y newtons is placed on the rod at B. We can see here written in red. And so its weight will act downwards. The rod is at the point of tilting. Find Y. Okay. So if you imagine that you push down or pull down with a force Y at B, and this is about to tilt, well, what we'll find is that the D will still exert a force. In fact, probably a bigger force as we push down in here, but it will tilt about D, and the contact at C, when it's about to tilt, will be lost. Okay, so the reaction force here will be 0, and then there will be a bigger reaction force here. So we can take moments about wherever we like, but the easiest is to take moments about D, Y, because then we don't need to calculate this reaction force here, and we know that this reaction force here will be 0. So if we take moments about D in this new situation when it's about to tilt, we have that the distance from D of Y is 2. So the turning effect will be 2y clockwise, and then the distance of W, now that we've worked out that X is 2.2, will be 1.8 from D, and we know the weight of the rod is 25, so the moment of W about D will be 1.8 times 25, but anti-clockwise. And so we get that 2y minus 1.8 times 25 equals 0, which means that Y equals 22.5 newtons. So the central thing here is that we know that when it's about to tilt about D, that the contact force at C will be 0, and therefore we only have 3 forces. And by taking moments about the point that this force goes through, we can then ignore what that force is. We don't need to calculate it, and then effectively we have only moments of 2 forces from which we can work out Y. Question 4, a typical statics problem, in this case a ladder. So ladder AB, shown here, of length 8 meters and mass 15 kilograms, is leaning at rest against a smooth vertical wall and on a rough horizontal ground at an angle of 60 degrees to the horizontal. Modeling the ladder as a uniform rod, that therefore means that the weight can be thought to act in the center, that is 4 meters up the ladder, and using G to be approximately 9.8 meters per second squared, find the reaction force RA at A. That's that one here. Okay, because the contact is smooth at B, we have no frictional force, so we just have a contact force which is perpendicular. At A, we have a perpendicular contact force, RA, but we also have a frictional force, F. And if you imagine that this ladder slips, it won't slip up the wall, it'll slip down the wall. And if it's slipping down the wall, then the frictional force will resist it. So the frictional force must be towards the wall. Even if this is not slipping, the frictional force will act so as to prevent motion or potential motion. So the frictional force is towards the wall. So we've labeled here all the forces and their locations. What else are we told? Yeah, okay. So the reaction force at B, how do we find that out? Well, the easiest is to take moments about a point. I'm taking moments about A. And the reason for taking moments about A is that then we don't need to worry about what RA and F is. We're only going to involve the weight, which we know, and RB, which we want to work out. So taking moments about A, the 15 kilogram mass of the rod acts as 15g weight, and its distance is 4 meters, but that's not a perpendicular distance. So if this is 60 and we resolve the 15g force perpendicular to the plane, then that will be this angle here, perpendicular to the rod. The angle perpendicular to the rod and the weight makes is 60 degrees. So the perpendicular force will be 15g cos 60. And then the distance will be perpendicular of 4. Or if you want to, you can resolve this 4 meters here and get the perpendicular distance of the 15g force. But either way, you get that the turning effect of the 15g force about A is 15g cos 60 times 4. And then similarly for RB, this angle here is 60. So resolving RB perpendicular to the rod is going to be RB sine 60. And then the distance, which will be a perpendicular distance to RB resolved perpendicularly, is just 8. So the turning effect of RB about A is RB sine 60 times 8, resolving either the force or the distance. And then because the total turning effect is 0, we can rearrange this to get RB equals 42.4 newtons approximately. And once we know that, we can now work out other forces. So if, for example, we want to work out the frictional force, if we resolve horizontally, the only horizontal forces are F and RB. We get that F minus RB equals 0, resolving to the right, and therefore F equals RB, and therefore F equals 42.4 newtons as well. And of course, we could work out RA if we wanted to by resolving vertically upwards as well. Okay, so these are the main principles that you need to know for moments, which are how do you take the moment of a force, which is perpendicular, how do you take the moment of a force which isn't perpendicular, how do you solve problems of things that are in equilibrium when they're in this situation here, or when they're about to tilt, and then a typical statics problem of a ladder is quite common in exam questions. I hope that's useful.